Good morning, ladies and gentlemen. Welcome to today's webinar. My name is Itumeleng Tabadi, a senior engineer in the Parametallurgy division at Mintech. I'm standing in for Isabel, our regular host. She couldn't be with us today because of additional commitments. Today's webinar is going to be presented by Dr. Quinn Reynolds, a technical specialist in the Parametallurgy division at Mintech. I hope you will enjoy the presentation as much as I know that Quinn is going to enjoy giving it to us. Quinn, over to you.
Thanks for the introduction, Itu. I appreciate it. And welcome to everybody who's joined us online today. I'm going to be talking to you today about plasma arcs in arc furnaces and how we've been using computational modeling tools to help understand them a bit better. I apologize, looking at the audience, it's quite a well-educated crowd, and a lot of you will have probably seen a lot of the content in this presentation before. So, but hopefully there'll be one or two new things and we can unpack them along the way in the questions. So sit back and enjoy, and if it's boring, please feel free to fall asleep. So, I work in the Parametallurgy division at Mintech, like Itu, which, as I always like to say, is all the people who like to play with matches when they were kids. Essentially, we do research into the treatment and processing of raw materials at high temperature, usually temperatures high enough that rocky ores and metals are molten, and we can do chemical reactions with them in the molten state. It's a really interesting area of study. There are a lot of challenges with which tools like computational modeling can help us address. Our focus is really on electric smelters and particularly direct current arc furnaces. I enjoy working with furnaces a lot because they're really grand challenge engineering problems with a huge amount of stuff going on in them. So, oops. Sorry about that. So to understand why we want to study arcs, it helps to understand, or it helps a lot to start off with a description of one of the common types of arc furnaces, which is a DC arc furnace. It's basically a cylindrical vessel. It's got a conical roof lined with refractories. At the bottom in the hearth, you've got an anode connection of some sort. In the roof, you've got some feed ports that come in, and you've got one or more graphite electrodes that come in the top. You might also put some of your feed down the middle of the electrodes if it's hollow. And inside the furnace, you've got a bath of dense molten metal. And on top of that is floating a bath of lighter slag. Those two are immiscible liquids, so they're a bit like oil and water. They form two separate phases. Power to your furnace, you connect the electrode and your anode up to a power supply, which converts AC electricity from the grid to DC electricity for the furnace using a transformer and rectifier combination. And finally, of course, to complete the electric circuit somehow, you need something to conduct electricity between the tip of your electrode and your molten bath. And that something is a plasma arc. And that's really the thing that we're going to be talking about a bit today, because it's what makes an arc furnace an arc furnace. So it's important to understand the arc and its behavior correctly if you're planning to build and design and operate pretty much any kind of open arc electric furnace. If you mismanage the arc and the bath region immediately around it, you're going to struggle to run your furnace operation correctly. Arcs are also pretty interesting things to study. Well, I think so anyway, but I'm a bit of an arc nerd, so my judgment might not be all that sound. But fundamentally, they're these really incredibly fast, hot jets of gas that have been split up into a soup of ions and electrons, and that makes them extremely conductive electrically. And the interaction between the electric current passing through the arc and the plasma fluid that it's made up of really creates a lot of interesting behavior, and that's what we're interested in studying. Unfortunately, large high current arcs are also pretty violent phenomena, which you'll know if you've ever stood next to one and try to measure what it's doing. All the hazards involved in studying real arcs really make running experiments and measurements on them very difficult indeed. And that means there are a lot of gaps in the understanding of fundamental arc behavior that we need to try and fill in. And one of the best ways we can do that is by building theoretical and computational models of the arc. And we can run those in our nice, comfortable offices where we have much smaller chances of being horribly killed, which is always good. Okay, so maybe let's take a brief look back at the history of arcs and arc modeling. The first descriptions of arcs really go back more than 200 years to the work of Davy and others. And although they were very poorly understood at the time, they were still used a lot for things like high-intensity lighting, arc lamps, and things like that once grid electricity started becoming widely available. So here's a nice picture of Davy demonstrating his arc lamp concept to a group from the Royal Institution in London in the early 1800s. It's quite interesting to see nobody's wearing any eye protection, so I guess health and safety were less of an issue back then. So once the physics and knowledge improved a little bit, models of the arc also started to improve. One of the oldest and simplest models just treats the arc as a constant voltage device. So regardless of the current that's passing through it or the size and shape or anything, the arc stays the same, or the arc voltage stays the same. So next came models that looked at some of the basic heat transfer effects in arcs, like Cassie's model, for example. And although they're still greatly oversimplified, the arc's electrical characteristics can at least respond to changing voltage and current in these models. And that makes them quite useful for working with AC arcs particularly, and they're still used today. So one of the first really fundamental descriptions of how arcs work came from Mecker in the 1950s. His analysis really laid the groundwork for understanding the interactions between the arc's electromagnetic fields and the plasma fluid that carries them via the Lorentz force. His calculations also laid out the square power relationship between the stopping force generated by the arc jet and the current that it carries. And that's an important correlation that's used in quite a lot of empirical models of how arcs interact with the molten bath of process material in electric furnaces. So later on, more advanced empirical models evolved, which take into account as much of the fundamental arc physics as possible, while still being mathematically quite simple. For example, Bowman's model defines a scale-independent arc column shape from empirical evidence. And just from that, you can then derive other electrical, thermal, and mechanical effects. And that Bowman model has actually proved to be remarkably accurate in describing the gross electrical behavior of DC furnaces at all scales. So much so that we still use it today to do quick sanity checks on scale-up for industrial furnace designs, for example. So once digital computers got good enough, it also started to become interesting to solve the fundamental governing equations of the plasma arc directly. These are the Navier-Stokes equations for fluid flow, the energy conservation for temperature, and Maxwell's equations for the magnetic and electrical fields. So Julian Zacchelli was really the pioneer of this approach. And he and his students and colleagues really developed the methods for computational solutions of furnace-scale plasma arcs in the early 1980s. These were obviously very simple and crude models by modern standards, but they gave the first taste of what could be possible using numerical methods. And of course, like everything else in the world of the integrated circuit, numerical modeling of arcs grew rapidly in sophistication, along with the exponential increase in the speed and power of computers. And there was a really lot of good work, and there were really a lot of good people working in this field in the 1980s and 1990s. And they continued to extend and enhance the modeling of arcs by adding in more realistic physics and coupling between fields, more sophisticated numerical techniques, and also more industrially representative model conditions. We really owe a lot to these people. A lot of what we do today is really just incremental improvements of the work that they did. So at Mintech, we were a bit slow. We only woke up and started seriously investigating computational arc modeling about a decade ago. One of the things we almost immediately noticed was that, as a lot of other people had discovered many years before, high current arcs are really dynamic things. They change and evolve into complex asymmetric shapes many times in the fractions of a millisecond. And this rapid changing really results in electrical and acoustic noise that is characteristic of arc behavior. And we wondered if we could study this a little bit more by exploring the one dimension that very few of the previous modeling efforts had looked at in detail, which was time. Okay, so how do we go about building computational models of these complicated things? Well, arc physics, as we mentioned, is controlled by three main phenomena, all of which interact with each other in different ways. So first and foremost, the arc is a fluid flow problem. As I mentioned earlier, you're going to need to start off with the Navier-Stokes equations in any of these models, and that's in order to describe the momentum transfer. And that's that top equation there. You also, of course, need an additional closure to fully define the problem in velocity and pressure, and that's provided by the mass continuity equation, which is the second one that's shown there. To complete the fluid flow description, it's important to include this vector source term, which is the Lorentz force, and that describes how electromagnetic fields interact with the plasma to move it around. Then the second component you need is the energy conservation equation. That governs all the heat transfer effects, so that's describing the temperature field in the arc. And again, to complete it, you need to include some additional source and sink terms for heat transfer by electrons, resistance heating as current passes through the plasma, and also losses by thermal radiation. The plasma radiation term is normally a really strong and nonlinear function of temperature and wavelength, and it's usually described using highly specialized numerical submodels for thermal radiation. Solving the radiation field can actually be the most expensive part of an arc calculation. It's quite hard to get right. And finally, you get to the last component, which is the electromagnetic fields in and around the arc. So we describe these using Maxwell's equations, and fortunately, we aren't at the timescales where relativistic effects are that important, so we can make a few simplifications to get the version of the equations that are shown there. So these are expressed in the magnetic vector potential A and the electric potential phi, which are the two fields we solve for. So all of these different field equations are very strongly coupled together. They form a single mathematical system which controls the arc's behavior. And that's what we have to try and solve numerically whenever we do arc modeling. So fun times. In addition, we've got another big problem. What you see here is called a continuum fluid description of the plasma. But plasmas aren't exactly a fluid with fixed compositions or properties. In fact, they're actually reacting mixtures, like the kind of thing that you get in combustion chemistry mechanisms, and they really can be ferociously complicated, just like those combustion mechanisms. That there is probably about the simplest possible example using a pure monatomic gas like helium, but generally the mechanisms are much larger. We need to somehow find a ton of extra information all about these components and the reactions between them. And then we need to do a totally impractical quantity of calculations on them if we want to correctly describe any particular plasma problem. So that sounds pretty insurmountable, but fortunately there are two really powerful tools that come to our rescue here. And the first one is something called statistical mechanics. This is actually one of the main pillars of modern physics. It's essentially a mathematical framework that describes the behavior of large collections of small things. In particular, it describes very fundamentally how bulk macroscale material properties emerge out of the quantum mechanical properties of the individual particles that make up that material. So in our case, fortunately, the individual particles are quite simple. At the temperatures we're interested in, they're mostly single atoms or ions in the gas phase. So the data we need for each one in order to do these statistical mechanics calculations is actually quite easy to find. It's tabulated in a lot of places. The second tool is a useful approximation in plasma physics, which is called local thermodynamic equilibrium. This essentially means that if the various chemical reaction processes in a plasma are fast and dominated by particle collisions, we can assume that all the species in the plasma, except for photons, are in thermodynamic equilibrium with each other. And that's generally true for arc plasmas, at least away from cold surfaces like electrodes. And that simple fact really lets us calculate the mixture of plasma species at any point in time and space purely as a function of the state variables, which are temperature, pressure, and initial composition. Once we have that mixture, we can calculate all the thermophysical properties we need using statistical mechanics. So our continuum fluid approximation for a particular plasma, all we need to do, we need to specify the properties as complicated functions of the local temperature and pressure, which we can do in advance. And we don't have to worry about doing all that complex plasma thermochemistry each time we need to know them. So in order to solve the arc equations numerically, we need to put them into some sort of mathematical computational framework. And at first we developed our own specialized finite difference solvers to look at arc dynamics because we needed to scale to extremely high resolutions in order to do direct numerical simulation calculations. After that, and also as our understanding of computational arc modeling got a bit better, we moved across to modern open source platforms like OpenFOAM, which is the one we use most heavily today. These open source systems are really good because they allow you to focus on your core expertise, which is, in our case, developing the arc models themselves. rather than having to worry too much about the fine details of parallel communication performance or solving systems of big matrices really fast, or any of the things that are important in making high-performance computing work. We sometimes play around with those things, but we don't have a lot of the heavy lifting has been taken care of for us. Okay, so let's have a look at some example results here. The fact that the arc is a synthesis of fluid mechanics and electromagnetic forces really means that there's a wide variety of phenomena which can trigger instabilities of all sorts of different kinds, often all at the same time, which is extra confusing. So a useful way to understand a lot of these effects is to run computational models of the arc dynamics, like these ones shown here, where you can actually see the instability effects visually and then compare them to reality and also to theoretical descriptions of those instabilities. Another useful thing with computational models is that they double as numerical experiments. You can learn things from them that would be hard or impossible to anticipate from the raw equations you're solving. So here's an example where we found that small and highly mobile anode arcs would form really easily on the anode surface in the model. When we went back and looked at our high-speed videos of arcs running on graphite blocks, we found examples of exactly the same effect. So that was quite cool. Another effect that comes out of the nonlinear nature of the governing equations is that the arc undergoes transitions in how it behaves in time. And those transitions are dependent on the parameters of the problem. So here's an example case where we changed the arc length and we saw a change in behavior between regular oscillations of the arc column and really chaotic, unpredictable motion. And we originally saw this kind of behavior in the models, as shown in the traces on the right of the voltages. And we really only found the transition effects in real life later when we started pointing high-speed cameras at some of our arcs. So another one of the things that we did with the early arc models was to take a look at the effect that the arc's rapid dynamics have on its electrical behavior, and whether or not we could use that to determine any interesting things from measurements of the electrical signal on real furnaces. It might sound a bit ridiculous, but it can actually be really difficult to know if you even have an open arc in an industrial furnace in many cases. We can only really measure things on the outside of the furnace, not the inside. So that turns out to be quite a challenge, but it turns out that you can get some useful information. The arc's motion causes quite a distinctive response in the frequency spectrum of the voltage and current signals, and we were able to use that response to design a detection instrument which we call DC ArcMon, and that can tell you whether or not you have an arc somewhere in your circuit. This can be quite a handy tool for indicating the presence or absence of an arc in cases where it's impossible to look into the furnace and determine that visually. So in cases where the arc region is obscured in some way by beds of feed material or banks of frozen slag, or it's just too hazardous. So another phenomenon which we have had a look at using computational models was the effect that irregular anode geometries can have on the arc's behavior. The arc doesn't always run on a nice flat surface. So here you can see the arc's partially blocked by a broken section of electrode lying in the molten bath right of center. And maybe contrary to what you might expect, with the electrode section in that position, the arc's actually a little bit more stable than it normally is. And that's because the geometry creates some really strong recirculation of the hot plasma back into the arc column. By contrast, you can see what happens to the voltage signal when the arc is running over an anode with lots of jagged edges. This is something you might get in, for example, a steel furnace when you're starting up over a pile of irregular scrap metal. Here, the motion of the arc's a lot more interrupted, and the resulting dynamics cause a lot of noise in the electrical signal. So we've also done quite a bit of work looking at what happens when fine dust particles are floating around in the gas around the arc. Since DC furnaces in particular often operate with very fine feed materials, the freeboard gases are heavily loaded with suspended dust, and that gets into the arc, of course. So this is a two-way coupling problem, because the dust load results in both a momentum and an energy sink in the arc model. And you can see that the chaotic nature of the arc jet really disperses the incoming dust in quite unpredictable and asymmetric ways before it settles into the molten bath, particularly in the arc region and the attachment zone. So another thing we've been doing quite a bit of recently is looking at how to link the plasma arc MHD models to multiphase fluid flow. This is again a really complex physics coupling problem, but it's an important one given that virtually all open arc electric furnaces operate with a molten bath of slag, metal, or matte, or some sort of material below the electrode. So in this case here, we've got quite a short high current arc, and the force of the arc jet is really punching into the slag layer and splashing it around to a large degree. And that's causing a lot of complex surface shapes that the arc has to try and attach to at any given point in time. And again, this is the kind of thing when we go back and look at these models in detail, we sometimes discover interesting things that weren't immediately clear from the governing equations. So on the left there, we're showing a 3D image of the slag surface with the shape of the arc cavity, as well as the electric current density at the surface of the slag. So here it's quite interesting to see how the current distributes over a much larger area than the physical cavity in the slag in this case. The two are not sort of coincident. On the right, we're showing the arc voltage in blue and the cavity depth below the electrode centerline in red on the graph. And here, what we're really looking at is that the cavity dynamics are at least an order of magnitude or two slower than the arc dynamics. So that means that to the arc, the slag surface is essentially frozen in place over short timescales. And to the slag cavity, the forces from the arc are heavily time averaged. So that sort of thing is already giving us some useful ideas about designing more efficient multi-phase flow algorithms in the future. So another big focus area for us recently has been integrating arc models with more realistic boundary conditions, which simulate the behavior of real furnace power supply circuits instead of using idealized approximations. This really lets us understand how transformers, rectifiers, and passive circuit elements like inductors can interact with the arc's dynamics. So here we've got an example of a 6-pulse rectifier system with no inductor choke at all in the circuit. And the model is calculating what happens to the arc during a single thyristor pulse cycle, which is the shortest time over which you can do any kind of power electronics control in your rectifier. So it's quite important to look at. Now, without any choke smoothing the current, the arc can either extinguish completely like this, or it can go into a positive feedback runaway or overload like this, where the current rapidly grows so large where it'll blow something up. If you're lucky, it's only a fuse, but if you're unlucky, it can be a whole bank of expensive thyristors or even worse. So these kinds of simulations are quite useful for manufacturers of DC power supplies when they're sizing circuit elements, and also when they're designing the control systems for the rectifier's power electronics. So, okay, that gives a bit of a flavor for the kind of stuff we're doing today. Of course, there's always a lot more that you can do with these kinds of models. So I thought I'd just give a quick look at the kind of things we're busy with right now, and also what these models could potentially be used for a little bit further down the line. So one promising area of research is looking at what happens near to the anode and cathode surfaces in a lot greater detail in these models. The properties of those surfaces and the plasma near to them is often a dominant factor in arc behavior. So it's good to know what's going on there in quite some detail. So evaporation and ablation of those surfaces due to the huge energy loads from the arc can cause additional instabilities, and it can also change the local thermophysical properties of the plasma. So we're busy working on models that can handle transport and chemistry of more complex gas mixtures rather than just assuming it's one uniform composition everywhere. Another technical challenge in arc modeling is the inclusion of compressibility and transonic flow effects as the arc becomes a supersonic flow at high currents. Now, exactly what constitutes high current in this case is still pretty much an open question. A simple scaling analysis would indicate that we should start seeing shocks appearing at around about 20 to 30 kiloamps. But quite a lot of the recent work on AC arcs suggests that big arcs can become a lot more diffuse and might only reach the supersonic regime at much higher currents, if at all. So regardless of when they occur, there's also quite a bit of conjecture about how shocks in the plasma would affect the arc's behavior. But in the absence of good experimental data at very, very high currents, computational models can probably start to provide us some useful insight here. And ultimately, of course, the real aim of a lot of this very fundamental research is looking at how to best transfer knowledge from the very complex, compute-intensive, and time-consuming computational models into more pragmatic tools, which can be used by metallurgy teams on plants, and also by design engineers who are working with real-time flowsheet simulators and things like that. This sort of thing is really very much informed by the fourth industrial revolution applications of computational modeling, which are heavily geared towards concepts like virtual prototyping, digital twinning, and things like machine augmentation of design and control of process plants. Of course, we also need some way of actually getting to the point where we can run those more advanced models. And as Scotty is fond of saying, one constant is that you always need more power. So let's do a little thought experiment. In computational sciences, we usually distinguish between a numerical model, which is essentially a low fidelity approximation of the governing equations of the system that we're interested in, and something called a direct numerical simulation. Now, this is a concept from fluid dynamics, but it's equally applicable to most other fields. It's basically your alpha and omega model. It's got accuracy so high that it actually matches all of the information you could ever theoretically possibly get out of an experiment, no matter how good it was. And it's important to know here that there are very strict mathematical definitions of what a DNS is, depending on what physics you're interested in. So it's a pretty extreme case, but we took a stab at estimating what the DNS requirements for a full-size industrial-scale plasma arc model might look like. And perhaps unsurprisingly, it turns out to be quite a lot. An exaflops is about 1 billion floating point operations per second, so that will take you quite a while to do on your pocket calculator. So is that a big problem? Well, there's something in computing called Moore's law, which I'm sure a lot of you have heard about. And that states that effectively that the number of transistors that can be crammed onto a chip doubles roughly every 2 years. And that also increases the performance of that chip by a similar amount. In high performance computing, we see that very, very clearly indeed. The top line there is a plot of the fastest supercomputer on the planet as measured by the LINPACK HPC benchmark since the early 90s. And the bottom line is the slowest computer on the top 500 list. So just to show the range. The y-axis is logarithmic, by the way, so that's why those look like straight lines. They're actually exponential growth lines. So now normally I'd have to spend a lot of time here explaining why human beings aren't very good at understanding exponential growth and how it always catches us by surprise and all of these things. But I think in the coronavirus era, we're all busy getting a very grim and practical object lesson in the realities of exponential growth. So just in case you were wondering, this is where South Africa's HPC capability sits on that graph. The red dots show the fastest computers available for public research at the Center for High Performance Computing in Cape Town. And you can see that we haven't been doing too badly in tracking the global trends. So what's interesting about this is that we can use this data to start doing a little bit of forecasting. If we go ahead and fit an exponential curve using the last decade or so of top 500 data, we get those lines there which show the fastest and slowest machines on the list. By the way, there's some quite good technical reasons why we only use the last decade, but I won't go into that now. So if we take those curves and extrapolate them out to the next couple of decades, this is the kind of thing we see. Here I've reverted to linear axes on the graph, so you can see the reality of exponential growth a little bit better. That gray band there in the middle shows the range we think we might need for a DNS arc model, that 1 to 2 exaflops range. And evidence from other industries suggests that you get really dramatic changes when you're able to start doing these kinds of DNS simulations. It can really turn your industry on its head. Instead of doing lots of experiments supported by a few simulations, your development pipeline can suddenly switch dramatically and disruptively to doing a lot of simulations supported by the occasional experiment. This usually happens in the gap between what we call capability computing. So that's the first time in history that a single machine exists that's actually capable of running your problem. And capacity computing, which is the point at which machines that can run your problem become fairly commonplace and accessible, and you can start thinking about running lots of variations of your simulations as a routine thing. So looking at arc furnace modeling, it looks like we're in for a bit of a revolution sometime in the next 10 to 15 years or so. The real danger of this, as it always is with exponential growth, is that it's tempting to dismiss these problems as being completely impossible to do until they're suddenly really easy to do, and you're caught completely by surprise. So the important message here is really that you need to be doing all of your preparation right down there while those curves are still sitting on the zero axis. Otherwise, when that revolution comes along, you're going to be left behind. That's exactly the reason South Africa went into a hard lockdown while we still only had a small number of coronavirus cases. If we'd ignored it until the numbers were really significant, it would have been way too late to act. And computing power is very much the same. It's a continuous, sustained revolution that's coming every day. And it revolutionizes everything as the waves of capability and capacity pass over you. And you'd better be prepared to ride those waves when they arrive for your industry, because the one thing I can promise you is that they will arrive one day. So that's pretty much it. Just some quick acknowledgements. Of course, Mintech funds a lot of the work we do in arc modeling and a lot of other really good, interesting research. And our research is supported really, really well by access to HPC facilities at the National Center for High Performance Computing in South Africa. So thank you very much to both of them. And thank you all for listening and tuning in today.
Thank you very much, Quinn. That was a really awesome presentation as always. To all the attendees, you're still more than welcome to send in any questions in the Q&A section. I've got a question from Lena Quinn.
Yes.
Lena Hockaday. Do you think that arc photography, which shows the visible spectrum of the arc, describes its behavior well? Would measurement or visualization of the infrared or ultraviolet spectrums add to our understanding of arcs? And can we visualize the magnetic fields around an arc?
Oh, okay, thanks, Lena. That's a very good question. Arcs typically emit in quite a wide range across the spectrum. Obviously, visible light is only a small portion of those. Typically, at the very high temperatures we're operating at here, a substantial part of the emission is in the ultraviolet rather than the infrared. So everything shifts to higher frequencies at higher temperatures. It would be extremely interesting to be able to visualize and do these kinds of high-speed photography investigations, for example, in the ultraviolet, but that would require probably some very fancy sensors and high-speed camera designs. It's something we should definitely look at. In terms of actually analyzing the spectrum, there's been quite a lot of work where people have pointed spectrophotometers at arcs in order to understand more clearly the spectrum and how it reacts to the arc behavior. Obviously, that's not coupled directly with photography, but it does give you information, more detailed information about the plasma species that are present. So in short, yes, it would be very, very interesting to do. It may not be the easiest thing to do. Visualizing the magnetic field would be fascinating. I'm not aware of any instrumentation yet that would let us do that for arcs.
Okay, that's great. I've got some additional questions. Lena is very thankful for the answer. I think she's very happy. I've got additional questions in the Q&A sections. One question from Harmon says, in case of shocks, what could be the frequency of shock waves and how would this affect the voltage and current?
Okay, so typically, Harmon, you're going to be probably looking at quite high frequency shocks just because of the high velocity and flow and the sort of late stage at which they come on. Essentially, arcs are such low density things that you really have to get up to extremely high velocities, kilometers per second, before arcs start to become significant, and they're going to be transporting at those kind of velocities or faster. Typically speed of sound kind of propagation. So I would imagine it's going to be quite high frequency behavior that you're going to see. And as to how it's going to affect the voltage and current, probably you're going to get a lot more high frequency noise coming onto that. My gut feeling, based on the modeling work we've seen and also evidence from large scale furnace operations, is that it probably has relatively small practical effects on the electrical behavior. But that remains to be theoretically proved.
Okay. And I've got another question from James Porter. Where is the actual point of heat transfer? Is it at the point of contact or along the length of the arc? Okay,
so this is a very good question, because it's one of the quite common misconceptions in arcs, is that when you look at it, or when you see an arc in operation, it's so overwhelmingly bright and powerful, it feels like all of the energy from the arc is coming out via radiation. But in fact, that is quite a small component that is transferred to the bath. The majority of the energy that the arc generates by ohmic heating actually is contained inside the body of the arc, and it's transferred directly to the bath below the arc by convection and local conduction. A little bit of radiation you'll maybe get. It depends obviously on the scale of the arc, but maybe you're probably looking at about somewhere between 0 and 30%. So the vast majority of the energy that's been generated in the arc is transferred into your molten material right where the arc jet contacts onto the surface.
Okay. The next question is from Abdullah. Are we able to model the change from diffusive arc to constricted arc? What about the division of one arc into smaller arcs?
Yes, so again, this is a good question, and it's still very much an open question. A lot of this relies on more sophisticated modeling of the electrode surfaces, particularly the emitting surfaces where the electrons are entering into the plasma. At the moment, in our models, we use quite simplistic approaches. We typically use constant current density approaches or just current density varying in time. There's been a lot of really good work done by the Reykjavik and NTNU teams in Scandinavia, where they looked at very detailed modeling of the electrode surfaces from a fundamental plasma physics point of view and generated more accurate boundary conditions. They're able to capture those transitions between diffusive and constricted arcs much more easily in those kind of models. There's also been some quite good work done by Loki in Australia, more at low scale or low current arcs for welding, but again, doing quite fundamental solutions of non-equilibrium plasma behavior near to electrodes. So yes, I think we're moving towards the capability of being able to model that implicitly. The division of one arc into smaller arcs, yes, we definitely are able to model that. And I think, again, it ties a little bit back to the electrode and anode contact surface models. But certainly we're able to capture that in a lot of our models. We can see the division of arc columns and rejoining of arc columns in the dynamics of the behavior. And that's one of the reasons why it's quite important to do dynamic arc modeling, is that you can start to see those effects.
Okay, there's a question and a comment from Stefan. He asks, have you integrated the slag electrical conductivity into your models to predict arc length? He suggests that this can be valuable in developing a process controller to control the rectifier and electrode position on arc length rather than arc resistance. Yeah,
this is also a really good question, and it's probably quite appropriate for the more empirical side of arc modeling. It's extremely important to include the slag bath resistance as part of your circuit model, is the short answer. Particularly for smelting type processes where your slag can be quite a resistive material, that can often be the majority of the voltage drop across the furnace. You know, you can have an open arc furnace that's actually operating much more like a resistance heating furnace in terms of its electrical response. So it's very, very important to include those. We do include them in our dynamic arc models, but generally in a simplified form. Where we include them quite explicitly is where we do the coupling with multiphase flow. There we have to explicitly model the potential distribution and the current flow through the bath. So those models do include both.
Okay, there's a comment or a question from Adija. He's saying that he sees similarity with fluid bed modeling, as we're not able to see what's happening in the fluid bed operating at high temperatures. What are your thoughts?
Yeah, no, I think it's a problem in pyrometallurgy generally, Aditya, as you well know, is that we have really, really complicated problems with huge amounts of physics going on that we don't really understand, and we can't measure anything. So that's it makes our lives quite difficult at the best of times. But certainly, I think there's potentially the same arguments for arc modeling, where we use computational models as proxies for experiment, can definitely be applied to things like high temperature fluid bed modeling. And in fact, a lot of that work is quite advanced in the energy generation industry and the synfuels industry, for example.
An additional question from James. Are there examples of more products than metal and slag?
Yes, absolutely, James. I think, we've certainly run projects at Mintech where we've seen things like, I can't remember exactly what the commodity was that we were smelting, but things where you can get, for example, multiple metal phases. So just different liquid phases in your metal. You can get metals that float on top of your slag and processes that have a dense metal bath and a light metal bath, and a slag bath or a matte bath in between. You can there are possibilities for very, very complex phase mixtures in the molten bath. We typically just focus on the slag and metal situation because that's in a way the simplest problem in smelting, and it's the one that you encounter most often. So yeah.
Okay, another question from Yolette. Given that the work has been done at pilot scale, with it potentially providing really useful information to producers, what would the ideal industrial test environment or commodity be?
So we've done some very limited testing at industrial scale on a ferrochrome furnace and ferronickel furnaces. But we need to do a lot more of that. I think the ideal environment really is a large industrial DC smelter. So not a steel furnace. It needs to be smelting a real commodity, and it needs to be running open arc, open bath, the traditional DC arc furnace kind of way of operating. If we could have access to that to install and set up an instrument that could run maybe for a period of time to gather data, that would help us enormously in designing DC ArcMon or making DC ArcMon more relevant for the industrial scale.
An additional question from Abdullah: how did you model the cathode spot size, or did you fix its size? What about the anode spot?
Okay, so it depends a lot, Abdullah, is the short answer. A lot of the earlier models, we would fix the current density. So we would specify a total current, and then we would fix the cathode spot size in the model based on the current density that was specified. Typically, we find those models they can give you some information about the arc dynamics, but there's a lot of dynamics that happen near to the spot that are quite important. And that's why we're putting a lot of energy now into developing better, more sophisticated, more fundamentally based models at the anodes, at the cathode surface, particularly. So we now have models that that essentially can move around. They can have variable current density across the cathode spot. In terms of treating the anode, we haven't quite gotten to that point yet, because we generally treat the anode simply as a constant potential surface in these kinds of models. But that would obviously be the next logical step, is to extend those kind of models that we're using for the near cathode conditions to the near anode conditions as well.
Okay, another question: can we model the motion of the cathode spot on the electrode surface? What about the size of the cathode spot? Can it be variable in the modeling?
Yeah, so thanks, Hadi. I think that's very much related to the previous question. It comes down a lot to the kind of boundary conditions you're going to apply on the electrode surfaces in your model. The modern models that we're using today do that. They account for motion of the cathode spot. They allow the spot to move around, and they treat an approximated version of the plasma physics near to the cathode spot. So it comes down a lot to a bit of a balance between computational load and accuracy. If you're willing to do a lot of very detailed modeling of the plasma behavior, the non-linear, non-ideal plasma behavior near to the cathode or near to the electrode surfaces, you can produce very, very accurate models of the motion of the spot. Generally, we find we've got to go to sort of semi-empirical models, which still allow a lot of those kind of behaviors, but let you solve everything in a reasonable amount of time.
Then there's a question from Lloyd Nelson on the 100 kiloamps DNS. When do you think you personally will have access to the computing power available to perform such DNS?
Lloyd, are you offering one? No, yeah. I always enjoy Lloyd's questions because he keeps me very honest. And whenever I stand up and talk about these models, the first thing he says is, when are we going to get one of these for an industrial scale arc? So, Lloyd, I think practically speaking, we're probably going to be waiting 10 to 15 years. The kind of access we have in South Africa for this kind of modeling work, we're not going to be getting the fastest machine on the planet to for our exclusive use to model arcs. I think that's probably going to be a little way down the line. But in the meantime, we'll build up the capability. We'll build up our numerical models rather than DNS models, and we'll work towards that process or that stage gradually. And once we get there, we'll have the tools ready to go.
There's a question from Jan Hendrik. Any developments on subgreat models like LES specifically for arc modeling?
Yes, thanks, Jan Hendrik. That's a very good question. In fact, we've been corresponding a little bit with a colleague of mine in Italy at Tanova, who's very, very experienced in LES modeling for combustion problems. And we've been bouncing around a few ideas of how we can build LES closures for arc models. Traditionally, it's extremely difficult to get a consistent LES closure for an MHD type of problem, due to the complex coupling of all of the electric and magnetic fields. Fortunately, it seems like in the case of plasma arcs, which are in plasma physics terms anyway, quite a low temperature problem, we can actually almost decouple a lot of the effects, and it looks like a lot of the standard fluid flow LES closures will be quite accurate. But we still need to do a lot of research on that. So that's one of the things in the pipeline.
A question from Suzanne. As you mentioned, it is very difficult to measure anything close to the arc. How do you then approach validation of your modeling work?
Excellent question. Yeah, you should always keep computational modelers honest by asking them how they validate their models. So in our case, Suzanne, it's primarily by doing almost second-hand measurements. So we rely a lot on electrical measurements. As I said, we've done a bit of development work with some of our colleagues on high-speed electrical measurements on DC arc furnaces. That really enables us to get quite high-fidelity information in the electrical signal that's coming out from a dynamic arc. And that information allows us to go back, compare against the behavior that we see in the models and see whether we see the same thing. So we can largely handle a lot of our validation with that, but obviously any additional measurements are always welcome. We've also done quite a bit of, if I can call it, qualitative validation, looking at the instability modes through photography comparison with, again, the results from the models. But it is a real challenge. It's not an easy thing to do, and a lot of the validation and testing we've done is at very low scale or very small scale. We have, this is again a question Lloyd often asks me, and it still remains an open question: is do arcs at 100 kiloamps look the same as arcs at 10 kiloamps or 1 kiloamp? And the honest answer is we just don't have enough information yet.
Great. There's a few more questions, Quinn. So people are really loving this topic. So, and we still have time, which is great.
Go for it, yeah.
The next question is it possible to couple the plasma arc model with a solid bed of bulk material on the bottom rather than a liquid bath?
Thanks, Alex. That's an interesting thought. We typically work in smelting furnaces. We're more interested in a molten bath because we're running continuous feed furnaces with an open bath. So generally the interaction between the arc and a liquid surface is more interesting for us. But I guess there's no particular reason why you couldn't integrate a sort of a conjugate heat transfer type of model, a separate domain model, and then model the lower surface in some way. I guess you could approach that in two sort of ways. You could either directly model the individual particles if they're big enough. That would probably be the most accurate approach. Otherwise, you'd have to go for some sort of continuum approximation of like a porous medium. But I don't think there's any reason why you couldn't couple it in. In fact, it would probably be a little bit easier than trying to do a multiphase fluid flow couple. So yeah.
Question from Willie. Considering the complexity of the arc correction, have you considered the oversimplicity and sometimes crude manners the electrode arm or holders are being constructed and controlled?
Yeah, I haven't, Willie, but that's an interesting point. I mean, I think one of the things we often joke about in the computational modeling business is we spend a lot of time sitting in our offices and playing with really nice sophisticated physics and maths, and then we go out into the plant and we realize that we're stuck with real world engineering. And I think that probably comes down to it comes down to the practicalities of how you actually get a DC furnace plant to operate reliably, consistently, and repeatably. I think it would be very nice if we could maybe design more accurate and more precise electrode arms, but that would always have to be traded off against the reliability of the thing. So you'd always rather want something that works crudely but well, reliably, continuously, rather than something that's very accurate but breaks every 5 minutes.
Okay. There's an interesting question from Adija. He's asking, any plans for modeling the no-HES arc?
Aditya, you'll have to clear that up for me.
Yeah, you can write a follow-up question to that one, Adija. Next question is from James Porter. You mentioned the value of modeling to guide the design for upscaling from pilot plant to industrial scale. Please comment on some of the pitfalls if this modeling is not done.
Okay, so yeah, James, this is probably quite a topic we could almost have a whole presentation on by itself, but I'll try and unpack some of the basics. Essentially, the main problem with arcs and arc furnaces is that the electrical scale up is quite non-linear and complicated. So if you're not at least doing some kind of modeling, and I'm not talking about necessarily advanced computational modeling, I'm talking about relatively simple empirical modeling, things like using Bowman's model and simple models of the slag bath. If modeling, you're very likely to get your electrical scale up very, very wrong. One of the problems in arc furnace design or processes plants is that when we scale up, we take very big leaps. So we don't have the luxury of building an 80% size pilot plant, for example. We'll often go from, you know, something that's maybe 2 or 3 megawatt scale right up to something that's 70 megawatt scale in one step. So we don't have the luxury of being able to take small steps and see that nonlinearity happening. So models are really the powerful link that tells you how you can take the information from your small scale and scale it up in the correct nonlinear fashion to the large scale. So that's the first thing that you're probably going to get very wrong if you don't do any modeling, is the electrical sizing of the furnace, getting the voltage and the current characteristics correct. The next thing that you're going to probably have trouble with is the heat transfer. So managing the fluid flow and heat transfer in the bath, the formation of freeze linings, the energy transferred from the open bath up into the freeboard and through your roof refractories and cooling systems. That's going to be challenging to get right without, again, some sort of simple model. It doesn't have to be a supercomputer computational model. It just has to be, you have to have a fundamental understanding of how the different modes of heat transfer work in order to get those scale ups correct. So that's just kind of two of the basic aspects. And as I said, we can probably unpack this all day, but certainly you do want to have some sort of basic understanding of how the furnace operates on a relatively fundamental level and how those affect the engineering decisions you have to make between pilot scale and industrial scale.
Great. Question from Benjamin. Would you be able to use the DC Arcmon to say something about the slag surface condition, like a foaming index crust on the slag surface?
That's a very interesting question, Benjamin. I think in theory, yes, you should be able to. I would expect it's going to be a little bit of a second order effect. And given that we already have quite a bit of difficulty just extracting the arc signal out of the DC Arcmon data, it may simply just be overwhelmed by the noise or need a bit more sophisticated analysis. It's definitely something that's come up before, and people have asked these kinds of questions before. You know, particularly foaming in furnaces is a very hot topic, excuse the pun, at the moment. So I think it's something that as we evolve DC Arcmon, we'll definitely start working towards looking at those kinds of problems.
Right, thank you. I think this was our last question. There's a couple more minutes, but thank you very much, Quinn.
Okay.
I think the questions raised a whole lot of subjects, which may be subjects of the next presentation from you, hopefully. Thank you very much. This was really insightful.
Thanks, and thanks everybody for tuning in. I hope you enjoyed it all around the world, and have a great day. Ciao.
Thank you.